Good morning, everybody. Today, speaking is going to be Everardo Olide, who is a PhD candidate in the Department of Applied Physics and Scientific Computing. Everardo works with Professor Daniel Siegel from the Mechanical Engineering Department at University of Michigan, and now is the chair at University of Texas, Austin. Investigating charge transport in battery materials and studying thermal energy storage in materials using computational methods. Everardo hopes to become a professor one day and to continue to do outreach work to get others excited about STEM. And he looks forward to having a fun discussion with everyone today. So please take it away.
All right, yeah, thank you for the kind introduction, Cassandra. So the title of my talk is Elucidating Polaron Hopping in Solid Electrolyte Materials. I guess before I go a little in depth, I could probably just mention, feel free to stop me at any point. We could just have the discussion as we go along. Some of the parts I did intentionally leave off just so that way we can have potential discussions if people are interested in some of those parts. But yeah, I'll begin. So as Cassandra mentioned in my background, one thing I'm interested in is energy storage, particularly batteries for this project we're going to go in. And so why do we care about batteries? So batteries are used in everyday devices, your phones, laptops, and one huge advent that people are looking into is basically continuing the electrification of vehicles, as current fossil fuels are consumed up to 1/3 right now within just transport itself. In order for us to basically make cleaner energy, we need to use renewables and sustainable forms of energy. One big problem with that, in particular with solar and wind energies, is that the sun's not always shining and the wind's not always blowing. So you need to store that energy somehow, and that's where batteries come into play. But kind of like with a lot of other technologies, there's been a huge stagnation in battery development in recent times. And so if we compare to Moore's law with computers, there's been a doubling in the computational capacity for computers every 18 months. But for batteries, there's no such law. The last big leap we've had was with the lithium ion battery, and that was in the early 2000s. So it's time for another battery revolution. And so one thing that we hope that could help us out with this is the usage of solid electrolytes in these systems, particularly making an all solid state battery. Currently, batteries use, at least the state-of-the-art lithium ion batteries, they use liquid organic electrolytes, which are flammable. And we all know what kind of led with that around like 2015, 2016 with the huge Samsung recall where phones were blowing up on airplanes, they were just catching fires. And even the large fires from Tesla vehicles. So they all use the liquid electrolytes. And so it's a good engineering tool, but it's just not as safe as we'd hope. These solid electrolytes also give us hope in enabling metal anode materials. And so that would be another large jump in energy capacity, about 10-fold from lithium graphite anodes currently. And so here's just a quick schematic of what we should think of in terms of an all solid state battery. So we have our negative electrode or the anode on the left. We have our separator in the middle, or our electrolyte. And on the right, we have our positive electrode or cathode. And so this is an oversimplification of how a battery works. But the key parts I want to highlight is that we need different properties on each of these parts. So on the electrodes, we actually want them to be good mixed conductors. And what mixed conducting means is that you could conduct ions and you could conduct electrons just as well. And so the reason why you want good mixed conductivity is because you want reactions to occur well on the electrodes while also transporting electrons through. And one reason why you want the solid electrolyte to be an ionic conductor, but not an electronic conductor, is that with the ionic conductor, that's how the reaction goes through. And by blocking these electrons from going through, you allow the electrons to go through an external circuit to do the work you want. For every electron that passes through the solid electrolyte, you're basically just burning fuel without any use. So you want to minimize this. So this is the ideal schematic, is that the conductivity for ionic and electronic are high on both the electrodes, but you want the conductivity, ionic conductivity, to remain the same in the electrolyte, but very, very low for electronic conductivity. And so currently the way that they construct most electrodes, in particular the cathode materials, when they're attempting to use solid electrolytes, is to mix some of the solid electrolyte with active materials, so the thing that reacts, with a carbon additive. So most, as you know, we'd hope is that the solid electrolyte materials aren't good electronic conductors. And so the problem with that comes in when you're making these catholites or a composite of the cathode, is that you're lacking some of the electronic conductivity you need in order to pull out from the reaction. And so this additional carbon kind of takes up space. And so every space that's kind of getting taken up is basically lost energy capacity. And so you could be making this more energy dense by, say, hypothetically, tuning this solid electrolyte material to incorporate electronic conductivity, specifically in the electrode regions where you have this composite. And so, you know, overall, we just want to attempt, can we really make these batteries safer and even simpler just by being able to tune this, and we don't have to have all of this additional additives. So before, you know, I kind of go more in depth into the talk and the additional things, maybe we want to understand how a battery works overall. So as I mentioned, you have a reaction that occurs on the electrodes. And so here's a simple schematic of a demonstration of a lithium ion battery, where you have lithium metal, which is a lithium ion plus the electron. Basically, the ion goes through the solid electrolyte and the electron goes to a current collector, putting in work. And in this case, I just have it lighting up a light bulb, but that could be your laptop or your battery or your vehicle. And the ion goes through to the positive electrode, and then the electron settles into a redox form, where it basically could, in this particular chemistry, it goes into a metal ion or the cobalt for a redox reaction. So there's two reactions happening on each end. And so currently the state of the art, what we know in terms of investigating this, is that, you know, these solid electrolytes aren't perfect yet, or else I wouldn't have research to do, right? So the one problem with solid electrolytes right now is that you still see some of this dendrite growth that you see in the liquid organic systems. The only difference is these don't catch fire, but they still get really, really hot, and basically you're losing your energy. And so Hana et al. Estimated that some of these dendrite growths really occur because there's still some electronic conductivity in the solid electrolyte material. And remember, we don't want solid electrolyte in the middle of the material, right? And so one question that we'd like to look at is, can we understand the parameters that lead to electronic conductivity in these systems? Like, in the sense that, can we engineer or tune this electronic conductivity in the solid electrolyte, in particular, lower it, right? And so, but we also have another question. We're in the region of the electrodes. We want it to be a good electronic conductor. So can we also tune it the other way? And so in this case, we just want to get a map where we can move around our tunability of where we want our electronic conductivity without hopefully affecting too much of the ionic conductivity. And attempts have actually been made in some prominent solid electrolyte materials, in particular this lithium lanthanum zirconium oxide system. It's a garnet structure. And this was done experimentally, where they doped some of this material. The problem was, from the 4 different elements that they attempted to dope it with, it didn't do the job. And, you know, they tried varying dopants, and some of them just didn't even form. They formed phase separations in the system. And so one thing we hope is, can we find a computational design to explore the space better, rather than just brute force experiment? And so the good hint about this is that people have already begun doing this for solid oxide fuel cells, where they study the conductivity in terms of dopants and other forms in these systems. And so there is hope to do this for battery systems. And so again, the overall questions we'd like to investigate is, can we understand the factors that contribute to electronic conductivity in these solid electrolyte systems? What are those factors? And can we get guidelines towards tailoring this charge transport in battery materials? And so before we could kind of dive a lot more deeper, we should try to understand, well, how does electronic conductivity occur in these systems, in these ionic conductors? So most of these ionic conductors, other than conducting ions, they're insulating for electrons, or they're semiconducting. And they can have various electronic transport mechanisms. So one of them that we're most familiar from our standard solid state electronics course or semiconductor course is that, or physics device courses, is a band conduction mechanism. And so that's where we typically have the bands, and you say, oh, you can add electrons to the bands, and then you have a effective mass, and that's what we're generally looking at. But there's also this other mechanism in ions, which is a hopping mechanism. So you could have certain sites where electrons or holes can sit on, and they could just hop from one site to another. And they could either hop onto defect sites or just some other sites that can have hopping. And so you can see from this arrow, you hop from one site of a lattice to another. And in some cases, this hopping mechanism is done via polarons. And so I'll go in depth into that a little bit later. So here's just a quick roadmap of what we're generally going to be looking at, is that we want to find a particular solid electrolyte we can investigate. We want to somehow study its electronic properties and hopefully create a design for tuning the electronic conductivity of these systems. So I basically just kind of chose one, and I'll only briefly touch upon it, which solid electrolyte we do, and I'll focus more on the attempt to study these electronic properties. I haven't finished my project to go on to the other ones, but more or less, we just want an adequate base of a model to study. We want to run some calculations to make sure our model's okay, and we want to examine this conduction mechanism in these solid electrolyte system materials. And so, surprise, this is one of the systems we chose, is the LLTO. So it's a lithium lanthanum titanium oxide. One reason why we chose this one is because it has a very high ionic conductivity, which is comparable to actually the liquid electrolytes that I had mentioned that were dangerous. And so this should be like a huge hooray, like, hey, we're on the right track. One problem is that this reacts very readily with metal anodes, which these are supposed to work with. So the problem is you end up changing the conductivity of the system and make it a good electronic conductor during this situation. And so that's bad for solid electrolytes, but it's good in our case because now we have a system that we know has been proven to be tuned in terms of having higher electronic conductivity and low electronic conductivity. And the structure is simple enough in the sense that it has a perovskite structure, which is cubic, and it has a octahedral coordination for the redox site.
Sorry, on the last slide, I was just, what are the fractions in the chemical formula?
Oh, yeah. So, so a perovskite generally has an AbO3 structure, and so right here in this top part where it has yeah, and I'm sorry, I should have explained this a little more. This Li, La, and this box, those are all technically the A part of the perovskite, and then this titanium is the B part. And so this blue atom right here, this is the titanium, and it has 6 oxygens around it. So you see, this is an octahedron shape. So it has 8 faces, and it has 6 oxygens on each part. And so it's kind of, you could think of it as like a diamond type structure. And on these corner edges is the A site, which is a lithium lanthanum, and this box is supposed to be a vacancy. In this simulation that I do, I don't have vacancies because I'm not interested in the ionic conductivity. And so this light blue, this light green atom is a lithium, this other one's a lanthanum. Red is oxygen, and inside this blue is a titanium. Yeah, did that answer your question? I'm not even sure if I.
Oh yeah, I guess I was just, I've never seen like fractions in the bottom. Like I don't really understand what it means to have like 2/3 of.
Oh, okay, yeah. So yeah, so I mean, I could technically multiply it by like whatever factor, and it increases. So what that basically means is this should add up to 1. So 3x plus 2/3 minus x plus 1/3 minus 2x. If you added this up, you see that this x's disappear. 2/3 plus 1/3 is equal to 1. So that's the A. And so you could actually tune the X factor.
I see. Okay.
Yeah. And the reason why you do that is because you want it to be stoichiometric and you want to conserve charge. If you actually deviate from this, in some cases, you can actually add more lithium. And in adding more lithium, if you fix this X, you actually add additional electrons to this titanium. And so you're tuning it in a different way, which one of the studies that I'll go into actually does that, but I won't talk about it too much in this specific talk, but we can talk about it in the question section. Yeah, good question though. Yeah, so what they're basically saying with that, with the fractions is, there's like you could think of it as a probability of having a lithium or a lanthanum in that site. So if you were to have X equals, say 1/6, which is the case here, 2 times 1/6 is 1/3, so you have no vacancies. 3 times 1/6 is 1/2. 2/3 minus 1/6 is 1/2 as well. So half of these A sites are lithium and half of them are titanium. Yeah. So does that answer your question more or less?
Yeah.
Yeah.
Thank you.
Yeah, great question. Yeah, thank you for asking. Yeah, and so in terms, so this was the model system we chose and decided. And so the problem with looking in the literature, which I'll highlight more right here, is that specifically for LLTO, no one has really done anything in terms of appropriately investigating the electronic conductivity. For the most part, a lot of these engineers looking at the system, they're like hyper focused on ionic conductivity. And so they've doped it for ionic conductivity. There hasn't been anything where they're like, oh, you know, I want to change the electronic conductivity. You want to suppress that. So they haven't really come up with the idea of like, hey, let's tune this, let's change it for other opportunities. It's been coming up more recent in recent years, but I don't go too much into those studies right now. But in terms of trying to understand this conduction mechanism, this study done by Emery et al. In 1999, they had actually they did DC measurements. So in order to actually calculate this electronic conductivity, you actually have to find a way to suppress or stop the ions. And so the way to do that is you run DC measurements by actually blocking this solid electrolyte with gold electrodes. So that way lithium can't transport through. And in running a current through it, the lithiums kind of get stopped by it and just kind of stopping it. So the only thing that could transport is holes and electrons. And so through this way, you can actually get electronic conductivity. And so they actually had suggested that there's a polaron mechanism. And I still haven't gone in depth into what are, I think I have gone actually into what are polarons. But what I say here is specifically small polarons. So there's different forms of polarons. These small polarons are very localized charges that are about a unit length long. And so there's also these things called large polarons, and these span closer to what would be known as through band conduction, because they're a little more, I don't want to say they're a little more delocalized. They are more delocalized to small polarons, but you could think of the spectrum of localization and delocalization as you have small polarons, which are very delocalized. It's within a site, you know, you have the distortion of the ions around it from about 1 unit length, and then it probably exponentially decays, versus a large polaron, which it could span even up to a couple hundred of unit lengths. And so it would be very large. The problem is these two have different dependencies based on temperature. So if, for those who might not know, metals, as you increase the temperature, the conductivity lowers. And this is because you're disrupting the free electron migration through scattering. And so, but if you compare to semiconductors, they generally have an increase in conductivity with temperature. And this is because as you increase temperature, you have more charge carriers, and scattering isn't as much of a problem, unless you dope very highly, which it then starts creeping into the metallic category. And so in this system, the reason why I showed this graph here is because it's very linear, and this is inverse temperature. So as you move to the left, you're increasing temperature. And this, as you increase, as the conductivity increases, as temperature increases, which makes you think it's a small polaron, which is closer to like semiconductors. And so this kind of gives a hint, okay, we can actually study this using the methods that I'm familiar with. And so a polaron, yeah, I hadn't gotten into what a polaron is. So a polaron is a charge plus, it's a charge plus a distortion, and it becomes self-trapped. So right here on this picture, you could think of having an electron, right? If I hold it together in a lattice, well, what would happen, right? If I have minus, what happens to the minuses? This is a pop quiz. What happens to a minus if you have a minus nearby it? Does it get closer or move away?
It would move away from the other negative.
Yeah, it move away, right? And so the positive, I could ask the question, but it's going to be the same thing. It moves closer, right? So if, did I lose connection?
Yeah, we can't see the screen anymore.
Okay. Yeah, it said unstable connection. I unfortunately actually had flooding in my apartment not too long ago. So hopefully this still works. Okay. Yeah, so if I'm to hold this charge right here in a lattice, if you could see that these empty circles, that's the original position of these lattices. You could think of a metal oxide where you have positive cations of the metals and negative ions of the oxygen, right? And so the oxygens get pushed away from this electron, and the metals kind of come closer. And what does that do to the potential of the lattice? You actually create a well that the electron now prefers to be in because it's more positive there. So this is called the self-trapping charge carrier. And this self-trapping with the charge is known as a polaron. So it's this distortion plus a charge localization. And depending on the range of localization, you call it a small polaron or a large polaron. And so here's an example of an isosurface of the charge density for an electron polaron. So if you can notice, the oxygens look like they're pushed further away from the centerpiece, right? And so this electron is actually localized in this case, it's a cesium atom. And over here is a whole polaron. And in this case, the whole polarons are actually localized on the oxygens, which are red. Yeah, and so our kind of weapon of choice to further investigate this is the usage of density functional theory. So maybe in terms of time, I'll probably just briefly go through this. For those who may be not familiar with density functional theory, we're basically solving Schrodinger's equation, but rather than dealing with the wave functions, we look at the charge density. And there was a theorem that was proved by Kohn and Hohenberg that there's a 1-to-1 correlation between the charge density and the ground state. And so basically there's only one ground state of a wave function and one ground state of the density. If you solve for the density, you solve for the ground state of the wave function. And so now, rather than solving from here, you can actually solve the Kaum-Sham equation, which allows you to go from a many-body problem to a single particle problem with an effective potential. So it's like, I mean, they won the Nobel Prize for this, so this is huge. The only problem is they didn't give us a hint for a solution. And so, you have to try to find a way to solve for this effective potential. Really quick, just the Kaum-Sham equation consists of like the standard, basically Schrodinger equation is just modified. You have a kinetic energy term, a potential term that's dependent on like the ion positions and part of the electrons. And then you have this exchange correlation, which just like lumps up all of the other stuff. And so this is the challenging part to solve for, the exchange correlation. And this is solved iteratively. Basically, you guess the charge density. So you can basically just literally apply like atomic density on each of the ions. and then you calculate an effective potential, as that's dependent on the charge density. And from that, you can basically plug it into the COM-Sham equation to get a wave function. From that wave function, you could then get the charge density as it's the effective like charge, the wave function squared. It gives you the probability of the electron density. And from that charge density, you could then start this iteration process over and over until the charge density and the wave function are about, they don't change much. And then from whatever you get at the end, you could calculate energies, forces, stresses, and a bunch of other eigenvalue problems for the system. And so, as I mentioned, they didn't give us a solution, so we have to use really good guesses for this. And I won't go too much into this right now. I'll mention it a little bit later. But for the most part, you basically guess this by assuming a uniform electron gas for like an LDA approximation in a local position, or a gradient with a generalized gradient approximation. So the thing is, you leave off like exchange and like real exchange and correlation, but through incorporating actually a Hartree-Fock method, you could incorporate exact exchange. So one problem with investigating polarons using the standard DFT methods is that in DFT, you tend to over delocalize these electrons. As I mentioned, you don't incorporate the a proper exchange or correlation. And so when you attempt to delocalize this in a real system, you'd see localization, but using this, you might not. And so you can't localize an electron to hold a polaron with this. The good thing is that there's solutions there, or else I wouldn't be using it, right? So one of the solutions is using this hybrid methods, which incorporates the Hartree-Fock exact exchange, and using a Hubbard term, or an effective Hubbard term, which is known as like a U, or DFT plus U. One issue is like, what value of U do we use? And that's something that recently I've run into that I might get a chance to talk about, given enough time. And so in terms of the methodology for creating a polaron in like these cells, I basically construct a supercell. And so this is an example of just a model. And basically I can add an electron to this system. And the problem with the system that I'm using, so I use VASP, which is runs DFT calculations, is it automatically smears it everywhere. And so you're not going to get localization, as it could fall into a local minimum of the system, even if it is preferred for it to localize. So then what I have to do manually is actually distort this system, kind of how a polaron would look like. And remember, if I push away, say, the oxygens away from a titanium, that's going to create kind of a more positive field in the middle. And once I kind of smear this electron over, after a while of running this self-consistent calculation, it will then localize in the middle. And comparing these two energies would give us a polaron formation energy, which is highlighted here. So this is actually the supercell system of the LLTO that I run. And in order to get the polaron binding energy, basically we want to say, okay, what's the energy of the delocalized one, and what's the energy of the localized system? And so the yellow right here is the charge localization in terms of spin. Right here, you can see it's delocalized across the whole system. The blue is just the spin down, yellow spin up. So in this system, it's just all like a spin up system. And you can see that it's pretty neat. It actually has the shape of what a d orbital would look like, right? It's in this case, it's a YZ. If we consider X, Y, and Z, it's an XZ d orbital, if y'all are familiar with those. And so, as I mentioned, I was tuning this U parameter, and we actually didn't have polaron formation until a value of actually, when we reran it and we changed it a little bit up, we had it from 3.4, but just for the sake of this, we actually have a linear dependency on localization. So remember, this is localized minus delocalized. The more negative a value, the more stable the localized part is. And one interesting signature that's noted that you can tell, like, oh, hey, maybe I got a polaron here or not, if you didn't have these charge density differences, is seeing a % difference in the bond length of your site compared to the delocalized case. So you can see here that there's a big jump in the bond distances. And so this actually is, you could actually see it using spectroscopy too. There's like XPS and a few different methods that you can do where It's very sensitive to the geometry of your system, and you can tell experimentally if you have this. It's just a kind of a small neat demonstration is that I ran a few different calculations from different starting points, and I actually had two different orbitals, and they actually weren't the same energy. So for a given value of 4.5, the polaron formation energy was actually different. And this was due to the higher energy state that actually formed here. And in this case, it ended up being a combination of these two, the YZ and XZ orbital compared to the XY orbital here. And as you can see from, you actually break the degeneracy because you bend the octahedron kind of down, and you have different polarons formed here. And they probably would have different migration energies, but I would only have time to test one of them. Yeah, just in the interest of time, I'll try to speed through this up a little bit more. So to kind of match the reason why we're discussing this is we want to be able to investigate the electronic conduction, right? And in this case, it would be via polaron hopping. And so in the late 60s, I believe, or around the 50s, Rudy Marcus, I believe, in chemistry, and a few other physicists at the same time had basically come up with a theory of conduction for some of these polarons. Actually, it might have been even earlier from a few physicists, because I know Landau had calculated some of these things too. But basically, the way that you can calculate a kinetic barrier is that you have a polaron from one site and you have a polaron on the other site. So right here, could you see my mouse? Let's see. So right here in QA, this is one site, QB is another site. And as you basically go from one site to another where an electron can migrate, you have an intermediate state where an electron is basically localized amongst both of them. And you have a slight distortion on these parts. And so if I was to capture kind of an image on each position from my simulations, I can get this kind of barrier. And from this barrier, I could then calculate migration barriers from this activation energy. And I could get conductivity if I know the particle number, which you can obtain from Hall estimates experimentally. And so this is kind of, I should drew this diagram up. So normally this lithium, lanthanum, titanium setup actually has a plus charge, a valence charge of +4 on each one. But if we have a polaron on one, notice I kind of distorted this oxygen further out compared to here. So we have a distortion here. And as I kind of move along in each of these snapshots, we have this electron cloud kind of migrating through, and you'd have kind of half and half on each titanium, and then it migrate back to the other one, which is kind of like a little movie. And so the first site was just here on this one site. The next one was on the bottom. And so these two are just different sites. And this is the intermediate state that I got. And what's pretty interesting is that you could again see that there's kind of a D-shaped orbital here. And in the oxygen, since it's kind of overlapping over and there's a partial basically occupation of this charge density in an oxygen, you can see that there's actually almost a p orbital here. And so I thought this was pretty neat, getting to see some of the orbital interactions of like chemistry or quantum physics in here. And so from just using a standard value of U, we actually got that some of the barriers were almost about half an electron volt, which is somewhat comparable to some of the other calculations of titanium oxide systems, which was about 1/3 of an electron volt. And we ended up varying the U value and to see how the barrier would increase. And so in this case, we saw that it increased almost linearly, and compared to some of the other studies, say in this case for titanium oxide, which is a similar system, it ended up plateauing somewhere after 10. We didn't go further enough to see if we ended up plateauing. But we don't necessarily want just a random dependency on this. We want to be able to make sure that this is more ab-initio, where we're just starting from a fundamental and we leave it at that. And so here's just another barrier to that. And you know, right now I'm currently going through the literature to finding out which are the appropriate values to use. And there's a few different methods to try. But one thing that's kind of a fault of the DFT plus U is you can't necessarily just match it to the band gap like you can for some other methods, because certain parameters still don't fall appropriately. I didn't go too much in depth into how this U parameter works, but it's basically adding a penalization of the Coulombic term on certain sites. And in this case, you apply it to the d orbitals of the titanium. But yeah, more or less from there, once we basically figure out what kind of barriers we want to use, we want to tune certain things. So we want to be able to maybe distort some of this lattice structures, maybe the anionic framework change to go from oxygen to sulfur, maybe to even some halides, and then try to just get a general picture of like how the chemistry is affected, how the structure affects these barriers, and we maybe even dope certain elements on some of these sites and see how that's affected as well. And so the hope is that we could come up with kind of like a table of a guideline, like if you want to come up with a material, tune the conductivity higher, you can use these elements. If you want to distort it this way, you can engineer it in another way. And so that's what we hope to come up with overall. And yeah, and so for now, that's the end of my talk, just so that way maybe we could have some questions for other parts that maybe others might have a question for. But thank you very much for listening. Yeah, thanks, Max. Yeah, thanks, Leah.
Wonderful talk. Thank you so much. I'm going to go ahead and stop the recording now, and we can take questions.